Welcome again to the NPTEL course on storage systems. In the previous class, we started looking at the Google file system. Okay. It's as we discussed before, it's a highly scalable system, and basically it is geared for performance, scalability, reliability and availability. So, we looked at some aspects of the Google file system, and we noticed that the Google file system has a specific idea about how to do things. One of them is that it takes care of faults in the system quite well, and another thing that it takes care of very well is it has a somewhat relaxed consistency model. And the idea here also is that you want to design your applications along with the file system. So, we are not assuming a POSIX file system, we are assuming something different, and for that reason this is it has got a relaxed consistency model. So, we will try to understand what this is today. Okay. So, you notice that some things have to be atomic. For example, if you are doing file create etc., that is, you create a file and also it has to be inserted into the directory atomic manner. If you do not do this, then it can create lots of complexities. Okay. So, now the file name operations or namespace operations are done exclusively by the master. It is not done by the clients. Sorry, by the clients. So, you need to guarantee atomicity and correctness of these operations, and that is done through locking. And this particular design, as I mentioned earlier, is a masters. There are masters and there are clients. Okay. So, okay, I shouldn't use about client. Okay, basically there is a master, and you have what do you call this? I don't remember this. It's various GFS clients. Okay, that's what that's the word. Okay, sorry, not able to remember the exact terminology. Okay, so so we've been calling a GFS master and GFS client, and basically the master's operation log defines a global total order of these operations. Notice that the ordering is an important issue because we discussed ordering sometime in the past, and what this particular system does is it defines a global total order, and then it is expected that all the GFS clients also notice this same. Okay. So, first of all, let us define what a mutation is. It is an operation that changes contents or metadata of a chunk, and the types of mutations that we typically talk about are writes or record appends. So, again, in regular file systems you just call everything a write, even an append is called a write, but in this particular system they have given two names, one is a write and a record append. A write is what? Write, the data is written at an application specified file offset, whereas a record append, it is appended atomically at least once, even in spite of concurrent mutations, but it is at an offset of the file system's choosing. Again, we discussed last time that we have this similar to fetch and add situation. Remember that in fetch and add instruction, many concurrent people are trying to increment something, and each party gets their own version of the incremented value, and it is there is no two people will get the same incremental value. Okay, something similar is what is going on here. Okay, so there can be multiple appends. Each append happens at a particular offset, and then this offset is chosen by GFS. Okay, and the order is not up to the client. Okay, so the offset returned to client and marks beginning of the defined region that contains the record. Now, what's interesting also is that GFS may insert padding or record duplicates in between. Why does it insert a padding? Because it may turn out the file that is being what is being written is going to span chunk boundaries. When you span chunk boundaries, then it creates some complications if you were to proceed, but you have to do work with 2 chunks now. Okay, so that creates complications. So the idea here is that if it so happens that the write is going to straddle 2 chunks, you don't try to do it within that chunk, you basically pad it, saying that there is just empty space, I move to a new chunk. That way the logic becomes that simpler. Okay? The idea is not to work with complicated things, just if there is anything which seems complicated, just defer the problem, make it simple and work with it. Okay? So you insert padding in case there is a write that straddles 2 chunks and work with only a chunk if possible. Okay? Also there could be some duplicates because of if some error takes place, then you can retry the operation, and sometimes there could be duplicates because of earlier attempts to write. Okay? And these have to be all detected. Okay? So basically the idea here is, even if there is something which is a duplicate, you need to recognize the applications or the application logic through a library, okay, code, then figure out that this is a duplicate. Okay. So again, this makes it for a slightly simpler design. If you look at the POSIX kind of systems, you don't have this kind of options. Okay. POSIX cannot tolerate these kind of things, okay, because the application is not, it's not been told that this kind of things can happen. Okay. Whereas in GFS, this is the model and the applications have to figure it out, and so that's why they will actually check for certain consistency conditions before they proceed. Okay. So it's the responsibility of the application. So if you do these mutations, then the state of the file after this mutation depends on the kind of thing that happened. Was it a success or failure? Was it concurrent? Okay. So GFS, they define some terminology, something called consistent and something called defined. If file region is consistent, if all clients see the same data, regardless of which replicas they read from. Okay, that means they always see the same data. Okay, so inconsistent means they see different data. Okay, usually you have failures that can happen. Okay, so consistent means all the clients will always see the same data. But this may not be what really is what you want also. What you want is something called a defined region. It means it is consistent and clients see what one attempt at write, in its entirety. So in a sense what is happening is that there will be multiple writers and you are getting interspersed writes from various writes. Okay, that will be called an example of a, if all of those things succeed, it will be defined, but it will not be, it will be consistent but not defined. Okay. So for example, when a mutation succeeds without interference from concurrent writers, the region is defined and consistent. Okay. So basically, clients see the mutation writes in its entirety, without any breaks, etc. Whereas a concurrent successful mutations leave region undefined but consistent. That is, all the clients see the same stuff, but they do not see the write in its complete entirety. Okay, it will be interspersed. So all clients see the same data, but it may not reflect what any one mutation has written. Typically fragments from multiple mutations. Okay, multiple writes are going on, concurrent writes, and then they can everybody sees the same data, every client, but what is there on the file is returned by different writes in some order, but everybody sees the same data. It's not one write incomplete in one entirety followed by some other write. Those things are not there. So if there is a failed mutation, it makes region inconsistent or undefined, and different clients may see different data at different times. Okay. For example, in one, let's say that there is some write going, multiple writes are going on, and some write was done, but one replica could not update its result because it failed at the time. Because it failed, it has the information of the previous content, whatever it was. So a write has gone to 2 replicas properly, but a third replica before it could be done, or part of it was done, okay, it died. And then right now it's possible that there is the proper write in 2 replicas, but partly only in other replicas. That way, that's the reason we are saying different clients may see different data at different times. Okay. The important thing is, again, it's this example of a cross-layer design. Idea is that applications should take control about the situation, the semantics, whatever the consistency guarantee is there. Look at the thing and decide. Okay. Again, this distinguishes from POSIX. Okay. But this is manageable because it turns out that mostly in this particular file system, appends are taking place, large files are being written. There is also checkpointing going on. So if a checkpoint happens, that means that you are in a very well defined state. So readers can always look at checkpoints and then proceed with it. They don't have to look at the current updates that are going on. Okay. So I know this, I think we'll go through it a bit more carefully. So the idea basically is that you can have it something consistent means everybody sees the same data, but it's not, it may not be defined. It is defined in case a particular write made it in its entirety, and it is, you can see very clearly that this write has, without being interspersed with other writes. Okay. Whereas if there is a failed mutation, what's happening is that some clients might see some information not updated because one of the chunks was down and it was not updated. When it came up, one of the clients can actually in principle see it. Look at this. So this is the model they have given in the paper. So you can have 2 different types of mutations, writes and record appends. Okay. Now if it is a serial, either it's a serial write or a serial record append, that means one after one, it's all completely serializable. Then if it's a success, then it is going to be what is the normal, the defined part of it, that is both consistent and it's also defined. Okay. Now in the case of record append, the reason why that is there because record appends are used as a way to attach something to a file without going through locking. One of the interesting things about this design is that they try to avoid things like distributed lock managers, DLMs. As you notice, DLMs are somewhat complex and they slow down the system quite a bit. So the idea here is, just like in the case of fetch and add, you basically want to allow multiple updates to happen in parallel. Okay. And the way they do it is, without a DLM, you are going to have concurrent appends going on. Okay. And this concurrent appends also can result in a situation where it is defined, but certain portions of the system of the file content could be inconsistent, again because of failures. Okay. So basically what happens is that you can have a record append going on, and some of the replicas, they don't get updated with the append because again the failure kind of situations. So they might have different piece of information, okay, because there is concurrency. See, there is no concurrency here, therefore there is no issue of it being any other than what has to be the case. So all these things are concurrent situations. Okay. Only this is a serial one. This one says serial success, but actually this record append, because it is essentially trying to give you a concurrent way of appending things. That's why you still could have the same problems like what concurrent writes also do. Okay. Okay, now let's look at concurrent. Okay. What is concurrent? You are writing multiple writes, and here you can have everybody sees the same thing, consistent, but it may not be defined in the sense that what you see on the file is not the write of a single write in its entirety. It could be partial here and there. Okay. So if there is a failure, you can have inconsistency because some guy has not, some particular replica has not updated, it's part of it, it has got old information, whereas other guys have updated it. So there is that inconsistency there. Okay. So again, we'll look a bit more into this, exactly how this happens and what are the ways to resolve the issues. Okay. The most important thing to remember is that failure is very clear. Some have not updated it, there is some old and new mixed up, okay, old information plus new mixed up. Okay. In the case of serial, it's very clear, it's basically only one party is updating it, and we'll see how you can ensure that if there are no failures, everything happens in the right way. Okay. If there is concurrent things, then again this can happen because of record appends, or it can happen because of writes, okay, concurrency. Okay. So what happens is that you retry the operation. When you retry the operations, you might have, what happens is that you are not given the offset. The client is not told if it fails, right? If you are told that it is something has failed, you don't give them the offset. So the client will retry again. So whatever has been written is actually junk. Okay. So you will have interspersed junk here and there. But finally when it succeeds, you get the offset. Okay. When you get offset, you know where exactly is the complete write. Okay. So that's why it is defined here, interspersed with some inconsistent information. Okay. So in the case of this write, you may find that it is consistent because all of the chunks are basically written in the same order. Okay. Basically the master actually has an order in which it is written, and all of them actually write in the same order. Okay. And that's why it is consistent. Okay. It can be undefined because the mutation is not written completely. Okay. Because if there is interference, then what will happen is that different writers will write different portions of the file, and therefore the region may not be complete with the applications can figure out what's going on. Okay. But it is not exactly the mutation written in its complete entirety. Okay. So if you have many mutations, the mutated file region is guaranteed to be defined and contained and returned by the last mutation. So basically, what is the way this is guaranteed is by making sure that all the changes to a chunk are done in the same order on all its replicas. Okay. And that means that there is some kind of a primary and the primary decides order and everybody else follows the same order. So it also uses something called chunk version numbers to detect any replica that has become stale because it has missed mutations while its chunks are was done. Because there are possibilities of failures, so a replica may become stale because it has not missed some changes. Okay, and to detect these things, you have version numbers. The version numbers will be able to can be used to figure out which replica is stale. I think this is similar to, again, if you look at NFS, we have some notion of what is called stale file handles. There you have something called generation numbers, and from there you can figure out if something is stale. Slight different model here, but it is something similar. Okay. So once some stale replica is there, it is never again involved in a mutation. Okay. Or given to clients that ask master for chunk locations. That means once some replica becomes stale, the master will essentially take it off as something to be given to a client. Okay. And the idea also is that these stale replicas are a problem and they will be garbage collected, depending on, we will discuss this in next class possibly. Okay. I am going through it in detail because this particular design has got lots of interesting ideas from various, all let us say well known ideas, but they integrated very well. Okay. So there is some garbage collection also going on for those stale replicas that have to be removed. So there is a small problem also, just like NFS, as client caches chunk locations may read from a stale replica is possible. Okay. So the window is limited, again just like in NFS, when window is limited by cache entries timeout and next open a file. When you open a file, by definition purges the cache from the cache all the chunk entries for that file. Okay. So if you really want to be sure about something, you just open the file, make sure everything is cleaned up. Okay. So most files are append only. I think this again we mentioned is the important part of the design. A stale replica usually returns a premature end of chunk rather than outdated data. So basically what's happening is that if you have a stale replica, you have not updated some things, you have not taken care of certain updates because the chunk server was down. So usually what happens is that you think that the file is this big, but actually it turns out to be slightly smaller. Okay. So if this kind of error takes place, okay, premature end of chunk, it asks for some size and it's actually not there, you get end of file or whatever, you can retry, the reader can retry and get the results get the information from the master about exactly the current state of issues. Okay. So the client may actually use a stale replica, but if it so happens that it tries to do something with it, it gets an error and therefore it can get the correct situation. There is also other possibility that component failures can corrupt or destroy data. Okay. So for example, some chunk servers might have failed, and these chunk servers failing are detected by heartbeating. What are heartbeats? Basically, these are messages sent from a master to other nodes to figure out if they are alive or not. Okay. And that is, so identifying failed server is done through heartbeating, but if the data corruption is handled by checksum. Okay. So every 64 megabytes has got a checksum and it has to match. Okay. When you read it, it has to match, otherwise you know that something is wrong. Okay. So again, if there is any invalid replicas, you need to restore them, and that typically I am told happens in 10 minutes. Okay. The only way you lose something is if all the replicas are lost. Okay. The important idea here is that data may be unavailable, but you are not given corrupt data. Okay. Under all circumstances, they try to guarantee that it's possible that you may not have access to data. So the application knows that something has not worked out, but it will not work with wrong data or corrupted data. That's one thing which they try to guarantee. Okay. So this application receive clear errors rather than corrupt data, and this is quite important because on the scale at which it is done, if you are at a petabyte level, it typically finds that there are about at least about 10 to 100 errors per day. Okay. These are what I call undetected errors if you don't do checksumming and other things. Okay. So if this kind of errors happen in critical parts of the system, then you might get the file system might get completely inconsistent. Okay. So it's a very serious issue. That's why at this level you need to ensure that there's already the disk is already doing lots of read Solomon coding, all those things. In addition, you're doing checksumming so that these kind of issues are taken care of. And again, one other thing is that the GFS is happening at the application level, right? Because it's closer to an application level system. So the checksum is happening at close to application level. That means that the checksum is happening with respect to both disks as well as network and all the transfers that are happening. Okay. So this is closer to an end-to-end design. Of course, it's only at the application level, file system level, not at the kernel level. Okay. But anything up till application, wherever it has come from, disk, network, HBAs, storage area network, networking hops, whatever it is, right? They all get, all the data will be, let us say, at the end only you check the checksum. So any error somewhere in between could be caught. Okay. And since there is a application and the file system are working together, the checksumming aspect is also, in a sense, almost at the application level. Okay. So there's some kind of end-to-end guarantee. So let's just see what is the kind of applications that you have to design with GFS. First, you have to depend on appends rather than overwrites. You have to depend on checkpointing, and you have to depend on writing self-validating, self-identifying records. Okay. Because things can go bad. When you write, you should write down in such a way that you read the data and then figure out what has to be done. Okay. Again, this is happening at the application level. It's not happening at much lower levels. Okay. So let's see what are the kinds of issues that take place. What is the typical use of a write? A writer generates a file from beginning to end, atomically renames a file to a permanent name after writing all data. Okay. And why is this talked about? Basically because the GFS itself is running on a Linux file system, and so it might be writing parts of a big file into various small files, so that recovery is easier. If something breaks, etc., you can recover from it, right? That's why finally, after you probably might want to take the chunks and make it to one single whole. That's why that atomic rename is sometimes may be necessary. Okay, after writing all the data. Okay, and one thing about reason why appends are used extensively is because appends more efficient and resilient to application failures than random writes. Why is it more efficient? For the same reason, fetch and add is efficient. So without fetch and add, what happens? Every time you have to somehow serialize every person, and everybody has to go through locking, right, one by one. When fetch and add, what happens is that lots of people are concurrently updating it, and everybody gets updated version one round trip. Same thing here also. That's why it's more efficient. Okay. So there's no distributed lock manager, and it is the file system takes care of the responsibility of taking all the updates and giving it some order. Okay. So the applications are not aware that they are doing any locking. Okay. That's one strong point. That's why it's more efficient. Okay. And it is resilient to application failures than random writes are. Okay. So basically, random writes, it turns out, have to do read, modify, write cycles. If you are doing anything in between, you have to do a lot of read, modify, write. With appends, the issue is slightly simpler, okay, because there is no the read modify write cycles are not really necessary. Okay. So the typical use is one writer generating a file from beginning to end and appending it. Okay. Or there could be many writers concurrently append to a file for merge results or as a producer consumer key. Okay. Now we will go into detail exactly how the append happens, but the important thing is the record append guarantees the following. It says at least append at once preserves. So basically each writer's output is preserved. Again, this we look at it is similar to in the case of NFS, we have this issue about what is called at least once, right. Again, that goes back to RPC. If you see this RPC calls, right, the RPC basically has semantics, either you can say at most once or at least once. At most once means either it is 0 or 1 time. Okay. Typically in RPC, people try to give you at least one semantics, and NFS is based on at least one semantics. That means that you try to do an NFS operation, it is at least done once, So there's a problem with, I think all of us, as we discussed before, with NFS, if you do at least once, then for non-idempotent operations, you get into a problem, right. So a special logging has to be done to catch those non-idempotent operations. Okay. Here we also have append at least once, similar to what we saw in RPC's at least one semantics. We have append at least one semantics. Okay. So in the case of NFS, we handle the problem using logging. Okay. Here it is done by looking at, if you see that there is something called self-validating, self-identifying records, right. So basically you write some sequence numbers, and that sequence numbers tells you whether this is an extra copy setting of the thing that has been written. Okay. So the application actually has to understand these things. Okay. It actually knows that these kind of things can happen and has to proactively handle it. Okay. That means if it reads the chunks, it can look at some metadata and know that this part of the file is okay, this region is not okay, this region is undefined, okay, and then it can essentially discard it. And then because it is self-validating, self-identifying records, it knows where the offsets are. So again, the chunk, there will be some information somewhere by which it can figure out that actual offset is here, even though physical offset is something else. So there's some kind of those kind of notions are all there. Okay. Again, the application has to keep track of all this. That's what I'm saying. Readers identify or discard extra padding and record fragments. Readers identify and discard extra padding and record fragments using checksums. Okay. So they have to do this systematically. Okay. So occasional duplicates and non-idempotent operations, readers ignore using unique IDs in records needed to name corresponding application entities for this web document. So again, this is an example of an application driven file system. If you want to detect, as I mentioned, duplicates, etc., there are some unique IDs in records, and these things are basically connected with the application level entities for web documents. So basically, it will have the information saying this is a web document X, part number 4, etc. So if you see two chunks or parts of a chunk with same part number 4, they know it's the duplicate. Okay. So just like we number pages, if you have duplicate pages, you can figure out their duplicates. We have to do the same thing here also. Okay. So in a sense, you don't go only by offset. You go by the offset, but also look at some metadata to identify that something is a duplicate. Okay. So the typical use is concurrent writes or single writer, and then there are duplicates of the things. You have to handle those things. But the other thing we can do is by checkpointing. Periodically checkpoints how much has been successfully written. Basically, when a lot of concurrent writers are going on, appends are going on, because of possibility that the thing can be undefined state, right? You want to use only checkpointed information. Okay. The checkpoint essentially is a consistent and defined part of the file. Okay. So basically, if you have checkpoints, it keeps readers from processing successfully written file data that is still incomplete from application's point of view. Okay. So even though it has successfully written it, it is still inconsistent. Sorry, I made a mistake. It is undefined. It's consistent but undefined. Okay. And the readers can avoid these kind of situations. They can essentially look at only things which are defined, not necessarily consistent. Of course, the standard thing advantage of checkpointing is that if something has failed, you can restart from the last checkpointed point. That's basically, you can restart incrementally. You don't have to restart from, basically it's a very long write, very large write, right? Then if something has broken, you go from the checkpoint rather than from the, and the reason why this is important is because it's a very large scale file system and you are talking about multiple gigabytes or terabytes at one go. So there is no way to provide atomicity. There is no way to provide atomicity because you don't have terabyte memories. There is no way to do it. So by definition, any large file of that kind, you have to break it up into pieces and write one at a time. The minute you say break it up into pieces, then atomicity of the whole thing is not possible. You cannot guarantee it. It's not possible. So you have to handle it through application, whatever else. Checkpoints can include application level checksums. Okay. Readers verify and process only file region up to last checkpoint, which is known to be in defined state. Okay. So defined means again consistent as well as the way a complete write has been written. Okay. So all the semantics of how to handle all these things is in the library code linked to applications. Okay. So I'm not clear, but they say that in the paper that except duplicate removal, everything is handled in the library code. Some of this is not handled. I'm not clear why. Okay. So this particular design is simple because it avoids concurrency issues because the appends basically take care of without locking it does it. Okay. So it avoids some of the concurrency issues because the file system guarantees atomicity of appends. Okay. And the consistency is avoided because you have a relaxed model. Okay. You don't have this stringent requirements that POSIX will have. So you basically sidestep some of the complicated things that are there, but the application becomes slightly more complex. But the idea is that the library code handles all of it. So the final application itself may not have to struggle that much. And according to this paper, which again I am not very clear, the duplicate removal is not handled by this library code. So that's the only thing that the application has handled. But that one can be simple because, as I mentioned, there are unique IDs in records. So as long as those unique IDs are something anyway you need to name application entities, and therefore if there is a duplicate, these unique IDs can be used to figure out that it's a duplicate. Okay. So again, as mentioned, there is no distributed lock manager required for this. Okay. For especially once you have atomic appends. Now let's look at how because we have multiple replicas, you have to figure out how to apply those changes to all the replicas. There has to be some order. How is this decided? Each mutation is performed at all chunks replicas, right? A replica by definition should have the same information like any other replica should have. Therefore, any operation that you do should happen at all chunk replicas. If it is a very large write or the write that straddles chunks, right? That is, there is a write which begins in one chunk and ends in some other chunk. That is at the boundary of 64 megabyte. Okay. To simplify the system, you break up the client code. Okay. Sorry, it's broken up by the client code. Sorry. Okay. The client code breaks up that write so that each write happens to be on the same chunk. So one way to do it is by padding. So basically what you do is you pad so that the chunk becomes full and then you can start with a new chunk. Okay. Or of course you can break up the write itself. Okay. For example, if it's a if padding is not efficient, it's not a good thing to do, then you can break up the write itself. Okay. So it uses leases to maintain a consistent mutation order across replicas. Basic idea here is you have a primary replica, and the primary decides how the updates are done in which order. Okay. So and the basic idea is that if in case the primary fails, the lease will get broken, because what's a lease? It's a lease is for the master gives one of the primary chunk servers, right, a certain period in which it can be the primary for all the replicas, and if it doesn't respond back or basically try to get the lease again, okay, it can give the lease to somebody else, or it's possible that the primary has failed. So because you have the lease model, even if the primary fails, then it won't reconnect with the master to renew the release. Therefore, the master can actually give it away to somebody else. Okay. It's a different, I think the important thing is that it's not as if it's taken a lock. If it's taken a lock, then you have to do something, you have to figure out how to ensure that the lock is broken, okay, which is a bit of a problem. Whereas the lease, it's only for a period of time. If it is not renewed, it goes away automatically, and the master is absolutely with a clear idea, it can give to somebody else. Okay. So master grants a chunk list to one replica, primary, and chunk locations. Okay. Basically what it does is, it grants a chunk list to one primary, and it also gives you where the chunk locations are, and these are cached by the client. So basically what happens is, when write is requested, we have to find out who has the lease and where are the chunk locations, okay, and this information is cached by the client. And the client pushes data to all replicas, and this data is cached, and then all the clients acknowledge it. Let's look at a diagram here for this. So this is a client here which is trying to do a write, and so first, if it is writing it, it has to find out who is the current leaseholder, if there is one. Okay. So if there is a current leaseholder, then that information is given back, that's the primary, or if there is none, it will take one of the replicas, the chunk server corresponding to that replica, and make it a primary and send it back. It also gives you all the chunk locations of all the replicas. Okay. So the client wants to write, so first it has to query the master to figure out who the primary could be, and the primary is decided by the master. Okay. Either it's a leaseholder, or the master decides who could be the primary, and then all the chunk locations. That's what happens. And then as soon as the client gets it, it starts pushing the data immediately. Now notice that this is similar to what we do in the case of, if you remember, we were doing virtual synchrony models. There you notice that there are two different things. There's some order in which some message goes to nodes, but there's a delivery order also. The two are different. Okay. You get the information, buffer it somewhere, and then the delivery order tells you in which order it has to be given to the application. Same thing here also. As soon as you get the information from the master about the primary and chunk locations, the client can push data to those replica chunk servers directly without waiting for a particular ordering. But once the data has been pushed out as soon as possible, because these are all large files, large chunks, 64 megabytes, etc., the idea is to push it to the clients as quickly as possible. The replicas, chunks, okay, as quickly as possible. And then later what happens is, once the data is already in all the replica chunk servers, then the write operation actually is committed in some sense. Okay, we'll look at that. Okay, how that happens. Okay. So client pushes data to all replicas. So immediately, without waiting for any ordering or anything of that kind, As soon as you figure out who the replicas are, you send it out immediately. Basic idea is to decouple data flow from control flow to improve performance by scheduling expensive data flow based on network topology, regardless of which chunk server is primary. Again, one of the things I have decided in this particular design was that throughput is important, very critical. Okay. So, the idea is that there is a control flow. Control is what? It basically tells you in each order something has to be updated. But there is also data flow, which basically tells you how to move these 64 megabytes or whatever amount of information move across the network. So, if you are doing big writes, you have to make sure that your network and is used to the best, it is in the best possible way. And the idea is that the topology of the updates, okay, should be determined independently from who is the primary. Okay. So, now the way the data is updated is based on the network topology. Somebody else is deciding. This guy is near to this guy, therefore you should go through him. For example, it might be that the primary is 2 steps away from the client, okay, whereas one of the replicas is only 1 step away. So, the way they do it is they send it to the first replica even though it is not the primary, and then that replica will actually in turn forward it to the primary. Okay. So, it is not done, it is not the way that you send to the primary and primary will send it to the replica even though the replica is nearer. Okay. So, this is not a good idea for when you are transferring large 64 megabyte chunks, for example, okay, or big writes, huge writes. Okay. So, they try to decouple the data flow from control flow to improve performance by scheduling expensive data flow based on network topology, regardless of which chunk is primary. Okay. Now, what happens is that, so at this point, the client has already figured out who the primary and who chunk locations are. The data has been pushed to all the primaries and secondaries. It has been pushed to all of them. Okay. Now, the write has not yet actually commenced. All that has happened is that whatever that has to be written is now sitting in all the secondaries and primaries. One primary and secondaries. The data is already there. Okay. Now, the write actually happens. Once the acknowledgement happens, comes back to the client saying it has written this data that had to be written. Okay. It had not made to the file, it just gone into a buffer in some sense. Some kind of LRU buffer is sitting there. That's all it has gone to. Okay. So, once all the acknowledgements come back to the client saying that data has been written, then the write actually starts, this part. Okay. Then it says the write command is sent to the primary. Okay. Primary picks a serial order for all mutation to chunk. Okay. Now, the client is telling the primary, I have sent all the data to everybody. Now, you decide the order and actually do the actual write. Okay. So, primary picks a serial order for all mutations to chunk. All replicas follow this order when applying mutations. Okay. So, write acts come back after the data has been transferred to all the secondaries and the primary. The client now sends a write. The primary now decides the order that it has to be, that the A has to be done first, followed by B, etc. Okay. Sorry, I made a mistake. There are multiple chunk writes are going on. Okay. And that is what is being ordered. Sorry, I made a mistake. Okay. So, you are having multiple writes, concurrent writes are going on, and you are ordering them, and each of those secondaries will actually apply those updates in the same order. So, every client will actually see all the updates in the same order. Okay. That is basically what it is. Okay. And this is possible because all the data is already sitting there. Just like in the case of our group communication systems, right, in the virtual synchrony model, there is, the messages are sent, they are going to be, let us say, buffered, and then based on the ordering model, whether it is total order or it is causal order, then those messages are given in the order that is specified by that model. something similar to happens here. Okay. So, and then once the secondaries have been told to write, then they will again respond by saying that I am done, that is what this is. And once the primary is done, the primary gets access from all the secondaries that they have done their updates of the chunks, then the primary again comes back to the client saying it is done. Now this can incorporate either done or something happened bad here, that is going to be an error out here, that also can happen. Okay. So, all the replicas follow this order when applying mutations. What there can be errors. Basically, write may have succeeded at the primary and some subset of secondary replicas. If it does not succeed at the primary itself, the whole thing is off. Okay. That is the obvious case. So, it may have happened at the primary, but a few of the secondaries, not everywhere. Modified region left in inconsistent state. That is the reason why we mentioned that it can be inconsistent, because some places have the new information completely, some have partly old information, some have partly old information. That is why it is inconsistent. Okay. Modified region left in inconsistent. Okay. So, client code handles such errors by retrying failed mutation. So, the client was the party who initiated the write, it again tries to write again. Okay. So, what is the model here? The minute there is an error, because only some party succeeded in doing it. Okay. You can retry the whole thing again. Okay. It might be because some data could not make it, so you tried resending the data, or it could be because some other errors. Okay. So, if you even after resending data, if it does not succeed, then you retry right from beginning. Okay. Because initially, how did we get started? We started with a client write, that is where we started. Okay. And it could have been broken up for various reasons. So, you are doing one thing at a time, and then again if you are unable to continue because of repeated errors, right, you try and see if you can start a new write. Okay. So, the file region may end up containing fragments from different clients, but replicas identical. Okay. So, our basic problem is that because of some of the errors, right, it may contain fragments from different clients, but you do not report success until all of them act back saying they finished writing it. Okay. So, that is why the replicas are identical. Okay. So, region may be consistent, that is everybody says the same information, but undefined state. In the case of failures, this will not even be consistent, it will be inconsistent. Okay. So, here is the case where we are talking about concurrent writes happening, which make the file region in undefined state. Okay. So, basically the global mutation order is chosen by the lease grant order chosen by master. So, it tells you who actually gets the lease, therefore, that decides the order, and within a lease serial numbers assigned with the primary, because the primary decides which order each of those mutations has to take place, because that serial number is here. Okay. So, basically if you have multiple concurrent writes, the way the master gives the lease decides who actually gets started, and then within the lease the primary orders various updates, okay, various mutations, and then that same order is followed by all the secondaries. Okay. So, there are two levels at which things are attempted to be controlled with respect to order. Okay. So, I think I will continue next with in next class I will try to finish the rest of the Google file system. Okay. there is a lot more things about list management, then issues about garbage collection and how to handle failures. Okay. Those kind of things also issues. So we'll talk about all this later. And hopefully they're done by next class will be done. Thank you.